To survive the winter, a predator has to isolate, exhaust, and bring down prey that often outweighs it by hundreds of pounds. This process looks chaotic, desperate, and entirely ruled by chance. But zoom out far enough, and the physical unpredictability of the forest disappears. Ecologists who were recording population data over decades found that these two species operate as a single system with mechanical precision. This chart tracks simulated moose and wolf populations over 200 years. The blue prey and red predator lines form a repeating wave. In each cycle, moose surge first. Wolves respond, over-consuming them until the moose crash. Then wolves starve and the cycle restarts. This loop is known as a stable limit cycle. In a limit cycle, the populations oscillate continuously within a fixed range, never reaching a flat equilibrium and never dropping to zero. They are trapped in a mathematical engine. This scatter plot maps wolves on the x-axis against moose on the y-axis. Stripping away the timeline reveals an unbroken oval. Every dot represents the exact population count at a frozen second. As time ticks forward, the system continuously orbits this closed shape. This consistent orbit suggests that the biological interactions in a forest follow a specific, repeating logic. To understand how that logic works, we have to reverse engineer the system's architecture. Decoding this system requires us to convert physical animals into abstract variables. The framework we use for this is system dynamics, a modeling method used to understand the nonlinear behavior of complex systems over time, using stocks, flows, and feedback loops. The core of this model rests on accumulators, which represent the physical count of the animals. In system dynamics, these accumulators are called stocks. A stock holds data, in this case, the exact integer count of the moose and wolf populations at any specific moment. These populations are constantly shifting as animals are born and die. They are driven by underlying rates of change. To write this formally, we assign our stocks a mathematical notation. Ecologists use the variable m to represent the current number of moose, and w for the wolves. Defining m and w replaces the unpredictability of a physical animal with a rigid data container. It is the mandatory first step to translating an ecosystem into predictable mathematical space. To understand why the cycle oscillates, we break the system apart and look at how each species behaves in total isolation. If we remove predators entirely, we are left with just the moose and their birth rate. The baseline rate at which a species reproduces is called its intrinsic growth rate, represented by the Greek letter alpha. Without wolves to calve a herd, a constant alpha drives the moose population into pure, unchecked exponential growth. Now we isolate the wolves. If we remove all prey from the environment, the predators are left solely with their natural death rate. This death rate is represented by the constant gamma. It defines the exact rate at which wolves die off without a food source. In isolation, the wolf population undergoes pure exponential decay. These two isolated forces act as the foundational energies of the system. The prey inherently explodes upwards, while the predators inherently collapse downwards. In isolation, both species either crash or explode. Therefore, the stable, repeating limit cycle can only exist because of the exact way these two volatile forces collide. The mechanism that forces these isolated species into the same ecosystem is predation. The wolves act directly upon the moose death rate. Modeling predation accurately requires us to calculate the exact rate at which these two species encounter each other in the wild. We calculate this using the law of mass action. The law of mass action states that the rate of an interaction is directly proportional to the product of the participating quantities. If you have 10 moose and 10 wolves, you multiply them to find there are exactly 100 unique possible pairings. Multiplication provides a biological failsafe. If the moose population drops to 0, 10 wolves multiplied by 0 equals an encounter rate of 0. The interaction ceases. An encounter does not guarantee a successful hunt. We apply a constant called predation efficiency to ensure only a strict fraction of those encounters result in a dead moose. That death does not just disappear. Every time the predator successfully hunts, the energy is biologically transferred. The moose death rate directly feeds the wolf birth rate. By multiplying the two variables together, m times w, we physically bind the fates of the two species. Their survival is locked in a shared equation, generating the continuous tension required to keep the system oscillating. The physical flow of animals and energy we just mapped out translates directly into standard calculus. These formal Lotka-Volterra equations track the rates of change. Equation 1 shows moose over time, positive baseline growth fighting the negative rate of predation. Equation 2 works in reverse for wolves, positive energy from eating prey fighting negative baseline starvation. These equations provide active instructions for a computational engine, determining exactly how the system behaves at any given millisecond. To start the engine, a simulation requires specific starting values. By setting the initial stocks to 200 moose and 100 wolves, we give the math a physical starting point. The calculus acts as the structural blueprint, but it is the computational simulation executing those instructions that actually brings the timeline into existence. The moment the engine engages, the software calculates thousands of microscopic changes per second. It checks the initial stocks, multiplies them to find the encounter rate according to the law of mass action, applies the constants, and plots the coordinate. This line graph is the raw, continuous output of those Lotka-Volterra calculations. It generates the exact 200-year stable limit cycle we observed at the start. We started by observing a mystery in nature. We broke that physical reality down into isolated stocks and flows, translating it into computable calculus. Today, scientists and engineers use mathematics as an active engine to recreate the precise underlying mechanics of our physical reality. Mastering system dynamics allows us to see the invisible, predictable mathematical architecture hidden beneath the chaotic surface of the natural world.